Good afternoon, everyone. Welcome to our coffee and compressed air. So finally, I have here a coffee. Usually we have it on the US time later, and today it's only me because I will be talking about very boring stuff. So it will be mostly on the uh, pipe sizing, the pressure drop calculations, and things like that. I'm actually a bit nervous to be alone in the studio. So if anyone wants to drop me here the hello, if you have any questions, just let me know. We'll have this recorded. But in the recent time, we had a few discussions about the oversizing, undersizing pipes. And basically, today, I just would like to go into the details and see how actually we have to calculate the pipe diameter and what it means. Does the bigger pipe, larger pipe impacts our system? How does it impact? And if you still stay until the end, I'll send you the link to our new online tool for the calculation of the pressure drop and calculation of the pipe. So here today I have some noise because it's my dog Douglas, who just joined our conversation. And perfect. So I just checked if I'm online, and let's start from the boring things. Grab your coffee, and I add to the stage my favorite slide that I think explains a lot of things on compressed air. And this is basically recently I got a question. Elvira, we checked the pipe, and no matter we realized that at some pressure point, at some pressure drop, the flow doesn't change. What is this? Well, this is my favorite things that I've been keeping talking about it, and I have a lot of videos on YouTube, so I'll also leave the link for that. It is so everything has a maximum capacity, right? So maximum capacity, maximum flow capacity, and you can just check the straw, see how much put the air through the straw, and you can see that the straw has this maximum capacity that it's actually limited by the diameter of the straw. Bigger straw you get, bigger capacity it has. And this capacity, it's not depends on the pressure. The capacity is not the flow that depends on the pressure, the volumetric flow. The capacity is the maximum mass flow rate that can pass the maximum mass amount of molecules that can pass through that. And this we call a sonic conductance. So if we take our test that I really love, and I think all the suppliers of the components such as valves and in any components that we call pneumatic resistance perform the test according to the ISO 6058. Imagine that we put here the valve, and then we have here the pressure 1 and pressure 2, and then we'll have a constant supply pressure. So once we invite you to our laboratory, that will be ready very, very soon in Italy, and we will be going to do a lot of nice workshops there, so live workshops in the beautiful hills of close to University of Benevento. We will perform this test for you. But now, just imagine this test in your head. So once you put here the maximum supply pressure, one constant supply pressure, and here you have the pressure regulator, and you start to change the pressure on one side and keeping the constant pressure on another side, you will create so-called the pressure ratio, right? So you'll have the pressure P2 to P1, and then it will be changing, and it will be changing from 0 to 1 because you can do the P2 only smaller than P1, simply because the flow will always go into the smallest pressure. So this is how the physics works. This is how our universe functions, as far as I'm aware for now. And imagine now that you start to decrease the pressure. So meaning that you are decreasing before you have here 5 bar, so you have 1, nothing is flowing. Then you start to decrease the pressure here, creating the pressure difference between those two pressures, and then compressed, the air starts to flow. It starts to flow until a certain moment it arrives the point where the flow rate, mass flow rate, doesn't go higher. And this mass flow rate, when it doesn't go higher, it means that we reached a critical pressure ratio where the velocity of the flow reached the velocity of the sound. So we are now in supercritical condition where no matter how we are turning this pressure regulator and changing the pressure after the component, in our pressure regulator, nothing will change. And this is called C. It's a sonic conductance. It's the maximum mass flow rate that can pass through this component. And now we're going to talk about the pipes. So the maximum flow rate that can pass through the component. And basically, this is where we have to work with. And we cannot go beyond the sound of speed, at least as I'm aware, also in compressed air systems, in our standard compressed air systems. And this is basically the C and B. Our sonic conductance doesn't depend on the pressure here. So it is a very wonderful parameter that we can use then to calculate the flow simply by just multiplying by the pressure. By the density that depends on the pressure. And this is a wonderful sonic conductance depends on the velocity of our sound. And depending on where we are, we can already calculate in different ways. So this is the super important thing. And when we actually talk about the pressure drops, the pressures, the sizing, oversizing, downsizing, our piping in the system, we always have to know what is the mass flow rate that is passing through the pipe, what is the maximum capacity of the pipe, not depending on the pressure, what is the pressure condition there, of course, and this also the critical pressure ratio for this pipe. So geometrically, what is happening there, or in this component, or in this pipe, where the geometrically this pressure ratio just achieves this critical sonic conductance in this point. And of course, for the piping, it's hard to optimize much the diameters or geometry. Usually this B is extremely important value for the suppliers of the valves. And now I'm already going into the lecture about this, but let's just, let me bring myself back and just think about the pressure drops and in general, where it is extremely important to calculate the correct sizing of the pipe. So, and for the pipe, the pressure drop, it's not the Darcy-Weisbach, it's not the calculations, it's not just one single diameter calculations thing. There is no one formula. You have to calculate always the C value for the pipe in compressed air, and always B value for the pipe. And I already had, I think we had our first coffee in compressed air where I showed the equations. And if you have questions, I can show you more equations about this. You also can go into the standard ISO 6358 Annex 3, where all these calculations are described. It's all validated, and trust me, it is correct calculations that consider the compressibility of the fluid. And it's very hard to calculate. So C and B for the valves, for connectors, it might be provided by the suppliers. And sometimes I think it should be provided by the suppliers and not just the volume flow rates. But anyway, the calculations of C and B pipes, they they're extremely important. So I want to share with you now the calculator, that online calculator that we created for for the pressure drops that includes this, but just let me show how this thing can, just share my screen. And I'll go and share the screen. Okay. So you can go into our direktineasybomb.com, and basically for the piping, what is extremely important, of course, undersizing piping, it will cause your pressure drop. So you can check the diameter for the optimization of the pipe. And here, for example, you see for this pipe diameter, for this pipe length and those flow rates and the downstream pressures. So we calculate the C, we calculate the B values, and then we can see if this is depending also on the temperature, on the material, and some other things, if upgrade needed or not, because of the actual pressure drop. So with the downsizing components, it's quite easy. So you also can check the pipe size, depending also on the pipe length here. But what we also had the conversation about, let me go back, and what is extremely important, I add again on the stage, there were some discussions, some comments about the what if the pipe is undersized. Okay, it's all clear, the pressure drop is too high, you need to remove it, so everyone knows that it has to be replaced, and this is a restrictive components. So meaning that the sonic conductance is not good enough for this application, for this mass flow rate. What if we go now and thinking the pipe is too big? And the pipe is too big, so imagine you actually simply physically, even if you have a big pipe, the most important thing that your mass flow just passes, right? So that your flow just passes there, that it handles this application. So from the pure physics point of view, it doesn't make any difference if the pipe is too big or it is too small. Only if you use it as the passage of the flow to some point of use until some pressure regulator. And here, but of course, there are the cost thing. There is like the extremely important that you need to have it's going to be more expensive. So you need to size it correctly. Sometimes it's even better to have a bigger pipe in case you're gonna, and I'm talking about the big distribution system from the compressor room, bigger pipe in case you want to add more production lines, right? So you're adding more production lines, and of course you need to have then it's better just to be on the safe side and have the bigger pipe. But here we go into a very interesting moment about some people will think, but I actually need to have all this pipe to fill it with compressed air, meaning that I need a bigger compressor. And here it is a mind game that you have, because I'll show you now where actually the pipe oversizing plays a role. And the pipe oversizing plays the role when we have a demand of the compressed air. So what I mean is demand. You have a point of use where the air is required, where the energy of compressed air is transformed into the mechanical energy of the moving mass, like in the cylinder, it transforms into the kinetic energy for blowing applications, for example, right? So those kind of things where we have an end point of use. And what we have usually there, we have, I don't have it here, but so this is my cylinder here, you see? And here is a long pipe that is then connected to the valve. And in order to make this cylinder move, I need first to switch the valve into the position when the supply air now goes into the cylinder, and then it goes into the pipe. So meaning that first we need to fill up all the volume here of the pipe, the dead volume of the cylinder, and then start filling the cylinder itself so it starts to move in order to perform this thing. Meaning, so you have the diagrams. So this is the stroke of the cylinder. You see that cylinders start to move, and it's just from A to B. So from 0 to 300 millimeters, this is the stroke of cylinder. This is the velocity of cylinder, right? So it starts to move here, the velocity starts to rise. Here you have relatively constant. Here's the end cushioning and stroke. So here you can ignore for now. It's a topic of 300 hours of the lecture about the exergy, my favorite topic. But let's go into the pressure. What is happening in the pressure chambers? In the pressure chambers is the pressure in one chamber. In the back is supply. In the front, it will be in the piston chamber, it's, let's say, 0. If we start from the scratch, the movement, by the way, those two lines, it's a measurement and simulation. So you trust me with our tools. And here, what is happening? So we have the pressure decrease in one side of cylinder, increase on another side of cylinder. It increase, and then we have it's decrease, decrease, decrease. So now in this chamber we have this supply pressure, and here it's decrease, 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 until the moment we reach the optimal pressure difference, and here will be 3 bar. That cylinder overcomes the all the pressure, all the frictions. So it starts to move. And here it starts to move at second number 1. Here you can see it starts to move second number 1. Here it keeps the pressure difference. Thanks to this pressure difference, this velocity is enabled, and this stroke is enabled. You see, it can be way more fascinating cylinder drives than we actually think. And what is important here about the piping? You see here the consumption. And here the consumption happens here, and then at second number 1, it happens here. So basically, this part is filling the volume, filling the pipe, and filling the dead volume. And here is the filling the volume of the cylinder. So meaning that bigger you pipe you get, more volume you need to start moving this cylinder. And this is a very big difference. And I think we need to have an article about it, that that this is so if you have any comments, if you have any questions, just drop me the message here again, in the comment section. So but what is here extremely important is that when we have the piping and compressed air system, it's extremely complex things, right? So when we have the piping that is used as a, I would say, as a passage through, we need to have a maximum capacity, maximum sonic conductance of this, in order that everything just like passes through this pipe. When we have an application and we have the valve that before something is happening in this end side of the application, the volume has to be filled, then this is basically, and then it goes to the exhaust. This is where the sizing is extremely important. Of course, you can go and think, okay, the piping in the main header, like from the compressor until the machine, it is also kind of a reservoir, but it's actually not. So it is the physically you have a demand side where the air is needed, and the air has to pass through this. And of course, the sizing of this is extremely important. So, and the oversizing of this might only lead to the higher, might only lead to the higher cost. However, we need always to understand what is going to be the maximum demand of this. But in order of the demand application, and we'll have a separate coffees and compressed air and everything about the cylinders, because it's and blow-in application and other applications, it's actually a lot. We can already discuss this part. So I hope this was useful. I still have a little bit of coffee here, and we're going to have it as recording. You always can come and check it. And I actually wanted to ask compressed air auditors in general, the oversizing of pipes, undersizing of pipes, what kind of experience you have with that? What are the issues you have with that? And I'll leave the link to our calculator. And if you have, it is a beta version, so we're still testing it. And but if you want to calculate the full system, please download our EasyCAS, and it's really easy. You just connect the components there, and you have a perfect calculations of this. I wish everyone a good day, and we'll see each other next week.